Hello, and welcome to the Mighty Pez's Rat Lab. In this video, we will follow along as I attempt to branch away from my usual breadboard and perf board circuits and try to learn how to make my own PCBs. Spoiler alert, you are watching this because I succeeded enough to be happy with the results and published this video to share my experiences. Hello, and welcome to my shop. In this video, we're going to be taking a quick break from the Rat Lab to come down and look at my newest toy, Genmitsu 3020 Pro MAX V2 router. There's quite a bit of difference between the V2 and the version 1 router, so I decided I was going to go ahead and unbox and show you this device as I assemble it, as I noticed that several videos out on the internet show the older V1 version. And as I mentioned, there are significant improvements and differences, so I thought it would be best to do a brief overview before working on the router itself. The purpose of this Genmitsu router is that I decided I wanted to take a stab at building my own PCBs. And yes, I know it's quite a bit cheaper to outsource that to various Chinese PCB manufacturers, but I decided that it would be fun to give it a try myself. And no, there's no very good reason for doing that. It is much cheaper to send off your PCBs for manufacture, but not having a good reason does not prevent me from buying toys and trying them out. So I'll be going over the separate components that came in the box. First, you'll notice the frame. It does have a manual adjustment on it, very nice, and an aluminum panel. As I mentioned, this is the 3020, which means 30 centimeters wide by 20 centimeters deep for the working base. Second, and the biggest difference you'll notice between the version 1 and version 2 is the components, the controller and the power supply are already mounted to the frame, as well as cable management is already in place. If you've seen any of the videos unboxing and assembly of the version 1, you'll notice that cable management was an afterthought. Dealing with the power supply meant that it was on the side and usually not attached to the frame unless you attached it yourself. And also you had to wire up and attach the controller yourself to the frame. This is a very solid frame. Also, before I move on, I will show you one additional difference. The version 1 had T-bolts, whereas the version 2, the screw holes are already drilled into the frame, so there's no need for the T-bolts from the version 1. Next, you'll notice that equipment comes with power supply, USB, an offline controller, so you don't have to plug it into your PC. Although in most cases, I will be running software such as Candle to control the CNC machine. There's a single piece motor mount. It comes with a 300 watt motor, a Z-axis probe, all of the mounting hardware that you will need, including the bolts, screws, feet, collet, and cabling. Also, it comes with a very good instruction manual. So let's get going and assemble this equipment.
Step 1, we flip the base upside down and attach the 4 rubber feet to the T-slot nuts that will hold it to the base. For step 2, we attach the frame that holds the motor and the electronics to the base with 16 screws. This provides for a very rigid structure. Step 3 is installing the spindle motor mount. We use 4 screws to attach the mount to the Z-axis carriage. Step 4 is installing the spindle motor. Now we connect the wires providing power to the spindle motor. Simply match up the red and black wires with the connector and lock each into place. Much of the wiring comes pre-installed, so for this step we only have to connect the Y-axis limit switch and the Y-axis motor. For all intents, we are done. I will connect and test the hand controller. I will not normally use this feature, as I will primarily drive the router from a Windows machine running Universal G-code sender. First, I test and reset the emergency stop button. Then we use the hand controller to jog the base in the Y-axis and the motor in the X and Z axis. Now, I will go learn how to use the software necessary to make PCBs. I chose KiCad for my PCB design software. Since this was all new to me, it was more of a random design choice and not an analytical choice. Nonetheless, it worked fine for me, but I won't be able to objectively compare it to other options. Within KiCad, we first use this schematic editor to do the logical design. At this stage, we haven't made any decisions on layout, routing, or pad sizes. An example of the logical design choice was to tie pins 1 and 2 together on each connector and pins 9 and 10. After the logical design is completed, we use the PCB editor to make all of our physical design choices. Design choices include the routing of the traces that connect the pads. And, for example, I chose to make the power and ground traces thicker at 1 millimeter than the remaining traces at 0.23 millimeters. The thinner traces had to be able to route between pads without touching, while the power and ground are designed to support additional current. Pad sizes and drill hole sizes were also defined in the PCB editor. I am now ready to export these design files so that I can then process them in another tool and generate the codes to control the router. We export the design files for the copper as Gerber format files and the drill files as Exelon format files. For the drill file, ensure that the origin is set to drill/place file origin and the format is Exelon. Then push generate. Then we will push the plot button to create the Gerber files for the routing. Now that we have created our Gerber design files, we need to convert it to commands to run our router. For this, we will use a program called Flatcam. Let's start by opening the file for our isolation cuts. Once loaded, we will select the file in the Project Files list and go to the Selected tab to find the properties. The settings that I will be sharing will vary based on your equipment, bits, and project needs. So please be aware that you will need to experiment to get the correct settings for your needs. A quick note, Flatcam defaults to inches as the unit of measurement. I was well into this project before realizing that Flatcam and the G-code sender can easily handle metric units. I decided that since I had done so many calculations already, I would not change midstream. For my next project, I will handle all units as metric. For this project, I used a tool diameter of 0.0075 inches to ensure all traces have separation. For number of passes, I chose a minimum of 3 to provide suitable copper separation. I then generate the geometry. This will generate an isolation cut file. At this point, you will review the tool paths to ensure that you don't have any missing cuts causing undesired connection between traces or paths. Notice how there is at least one red line denoting a cut between separate copper traces. There we will open the Gerber isolation file, select that file, and again go to the Selected tab to find the properties. First, we set the Z-cut, or depth, to negative 0.0015 inches. Increase the feed rate to 5 or more. Set the spindle speed to 10,000 RPM. This varies by router. And I generate the file. Again, review the drawing window to ensure that the isolation looks good. And we go back to the project list. Select Gerber Isolation CNC file, GBR ISO CNC, and go back to the selected files. The export G code will then write the output to a file suitable for loading into the router software. In my case, I will be using Universal G-Code Sender. There are options for creating the board cutout. You can use the cutout file generated by KiCad, but in this case, I chose to have Flatcam generate my cutout. So I go back to the project file list and select the original Gerber file that we started with. This time we go to the board cutout section and go to the selected file properties. These properties will be user preferences or project specific. I set the margin to 0.1 inch and the gap size to 1/100th of an inch. Now generate the geometry. I go back to the project list and select the cutout file. Set the cut Z to the required depth. My PCB is approximately 0.058 inches in depth, so a setting of minus 0.06 would produce a clean cut. But I chose a slightly shallower depth at minus 0.05 and trimmed the board with an X-Acto knife. Again, set your desired feed rate. I select multi-depth so that the bit takes multiple passes and doesn't work as hard. Here I set the depth per pass to be 1/2 of the desired cut depth, and I generate the file. We go back to the project list and select the GBR_cutout_CNC file. Go to Selected and export the G code. The last step is to load the desired drill file. In this case, my data is in the PTH or plated through hole file, even though my DIY board has no plated through holes. Again, we enter the cut Z depth. I originally chose a Z depth of 0.06 inches, which is slightly deeper than the board, but that wasn't deep enough. 1/10 is overkill, so 0.08 inches would have probably been perfect. I set the feed rate to 5 or higher and the spindle speed to 10,000 RPM. Generate the file. Select the new DRL_CNC file from the project list and export the G code. And now we have all the files we need to mill a PCB. Let's review some of the consumable items used during the milling process. Of course, the primary item is a blank PCB. For this project, I am using single-sided copper. My bit of choice is a 60-degree dual fluted vbit with a 0.2 millimeter tip used to mill the PCB copper layer. In addition, I use a 1.5 millimeter end mill for the edge cuts. And a 0.7 millimeter end mill for drilling the component through holes. It is recommended to use some sort of lubrication to increase the lifespan of the bits, and it also significantly reduces the copper and fiberglass dust ejected into the air, which can cause a lot of mess. I use Tap Magic Pro Tap cutting fluid, but mineral oil can be used as well. I use a Q-tip to spread the lubrication evenly. I use a good double-sided tape to secure the PCB to the wasteboard. Keeping the PCB from shifting during the entire process is critical to the precision milling. I also have a webcam I call R2D2, so I don't have to stay at the router during the entire process. Additionally, I find an accurate digital caliper to be very useful for verifying PCB thickness and bit sizes. Of course, safety is an important precaution. I wear a good dust mask and safety goggles whenever I am near my mill while it is operating. Wearing gloves and washing your hands after working with the oil or operating the mill is also a very good precaution. We have the Z probe circuit hooked up to the spindle and the copper of the PCB and are ready to kick off the height mapping process. PCBs, especially the cheap PCBs I buy, are very imprecise and have uneven warping that will lead to poor trace routing if not accounted for. With common copper thicknesses measured in the hundredths of millimeters, it doesn't take much warping to ruin your PCB. This process will test the Z height over a grid on the PCB and use this map data to adjust the G code to account for the imperfections. The way the probing works is that the software will move the bit across the grid in the XY axes. At each coordinate, it will lower the bit in the Z axis until the bit makes contact with the copper, closing the circuit. I will apply a little of the cutting fluid to the PCB and ensure to coat the area to be milled evenly. Note that the oil is penetrating the wasteboard, so ultimately I will be testing non-porous alternatives for my wasteboard. Now I will replace the vbit with the bit that I will use for drilling. Then we load the G-code with the drilling instructions into UGS. With every bit change, I must re-zero the Z-axis. I again replace the bit, this time with the one I will use for edge cuts. Again, we will zero out the Z-axis and load the program into Universal G-code Sender for performing the edge cuts. Here is the result of two different attempts to mill the circuit board. The main difference is that for my final attempt, I reduced the drill holes to 0.7 millimeters to provide a more snug fit for the pins and provide a little more copper to the pads for soldering. I am very pleased with the fine detail produced. Before we call this experiment good, I want to do a little testing first. As my goal for this little 10-pin backplane bus demonstration project was to determine if I could scale it up to a much larger project. I need to prove that this little home-built bus will be functional enough to support at least a 1 MHz minimal homebrew computer. For testing, I've made a little breadboard circuit consisting of a 1 MHz low-speed clock and an 8 MHz high-speed clock. I need to verify that the output will cleanly drive TTL logic levels. Each of these clocks will drive a separate line, and we will see how much noise or crosstalk is observed. We can observe that the clocks appear reasonably clean, much cleaner than one might expect to see on a Sinclair ZX81. And will likely be more than suitable for my needs. Removing the plot for the 8 MHz clock, we can see some ringing on the 1 MHz line, which corresponds to the 8 MHz cycle. So we know that somewhere in the circuit there is some crosstalk. Removing the 8 MHz signal completely results in a clean 1 MHz clock signal. Removing the bus from the circuit and measuring directly from the breadboard, we still observe some crosstalk from the 8 MHz clock on the 1 MHz clock line. So I'm going to assume that this is not all introduced by my PCB, and we'll delay learning transmission line theory for another day.
As a beginner, I am very happy with the outcome and expect that I can produce even more complex designs with practice. I would actually say that the Genmitsu 2030 produces a very acceptable PCB for the price. I want to be very upfront. There was a learning curve for me. I spent many evenings learning the various software packages and testing many bit spindle speed, bit depth, and process options. This process may not be quick and simple, but if you enjoy the learning experience and have a modicum of patience, producing your own PCBs can be rewarding. But please note, if you are doing this for any other reason other than personal satisfaction in the art, it will likely be cheaper and easier to use your favorite PCB manufacturer of choice. As I am possibly the only YouTube channel in this genre not sponsored by our favorite PCB manufacturer, I will likely continue down my own learning path and do my own PCBs in the future. Thank you for watching.